Alright, let's try this one. So on this one we're going to try our ratio test, or check out consecutive terms, the absolute value. In this case the absolute value really does something. It gets rid of this piece. That's kind of annoying, the oscillating sign here, alternating. So let's do it. Talk is cheap. So a n plus 1 all over a n, and I'm doing absolute values. That would be equal to, I gotta do the n plus 1 first. So wherever I see n, first of all I'm ignoring that because of the absolute values. Just go with those. So it'll be 4 to the n plus 1 times n plus 1 factorial square all over 2 times n plus 1 factorial. That's just the top where you are plugged in n plus 1 wherever I see n. I have to divide that by the bottom, so I know I'm going to have to flip it because I've done this a few times already today, so I know that's going to look like this: 4n times n factorial square. That's my ratio of consecutive terms. It looks scary, but it is so not scary. Could do this all day long. Alright, so here I'm going to break it up a little bit. This means 4 times 4 times 4 a bunch of times, n, and then one more time. So it'll be a 1 4 and then n more 4s. I write it this way because I'm looking one step ahead. I'm going to be able to cancel with that one. This becomes n plus 1 times n factorial, and that whole thing is squared. That's that piece. N plus 1 times n times all the numbers that follow it. All that over 2n plus 2. This piece right here is 2n plus 2 factorial, which of course would give you 2n plus 2 times 2n plus 1 times 2n factorial. And that's that piece right there. Now for the other part, I'm looking at 2n factorial over 4 to the n times 4. Whoa, man, I seriously got to figure out the back button on this. Times n factorial square. Alright, this piece right here, let's do some canceling here. This piece will cancel that piece because it's square there. This piece would cancel that piece would cancel that piece. After all the canceling is happening, got a canceling party going on. What's left over? I see I have a 4 here. I see I have an n plus 1 square there. By the way, just before I forget to tell you, every once in a while you go through all this song and dance and you get that r is equal to 1. If you get that r is equal to 1, then the test is inconclusive. You get an indeterminate form, and so you've got to try some other test. I'm just warning you, just in case we get 1 here, it'll be super fun. So alright, so then what do we have on the bottom? So then you have on the bottom you have 2n plus 2 times 2n plus 1. Okay? And that becomes 4 times n squared plus 2n plus 1 all over 4n squared plus 6n plus 2. And that goes to 1, and yippee-ki-yay. Haha, this problem turns out to be where the ratio is 1, and therefore the test is inconclusive. And you say, now what? Well, now we have to try a different test. Alright, so this is fun because then we get to pull out the big guns here and try something else. This part of the test failed, so therefore the test is inconclusive and we're forced to think of a different method. Now this reminds me of something incredibly powerful. I usually don't like to share this with people, but I like you guys. I'm going to share something with you. There's a famous estimate for n factorial, and the famous estimate goes something like this. Let's get a clean page here. The famous estimate goes something like this: n factorial is approximately equal to n divided by e raised to the nth power times the square root of 2 pi n. Duh. It's super famous. It's called Stirling's approximation. This is super powerful. Don't pull this out unless you need to. See if we could say something about this series using this estimate. So this tells you that this roughly looks like, let me think, it'll look like 4n times n factorial. I've got my estimate for n factorial there. It's n over e raised to the n times the square root of 2 pi n. That squared, all that over 2n factorial. Well, if I've got an estimate for n factorial, I can also get an estimate for 2n factorial. It goes like this. Blah factorial is approximately equal to blah over e raised to the blah times the square root of 2 times pi times blah. So if all I gotta do is plug in 2n for my blah there, that would give me 2n over e raised to the 2n times the square root of 2 pi times 2n. Duh. Now what? Well, fear not. Let's just keep doing it. So this becomes 4 to the n. That's that 4. I've got 2 of these here, so that becomes n over e raised to the 2n, because 2 times n gives you 2n, times the square root of, oh no, there's no more square root, because I've got a square there, so the square of the square root would just give me 2 pi n, all that over, this gives me 2 to the 2n times n to the 2n all over e to the 2n times the square root of 2 pi times 2n. Yeah, so this cancels with that, because the 2 to the 2 part, I could just think about it this way. 2 to the 2 is 4, 4 to the n is 4 to the n, allowing me to do this nice thing here. Cancel that. But wait, there's more. N to the 2n, that's exactly this piece right here. That's that piece. That's gone. But wait, there's more. The 2 cancels with those 2. And we get that this is approximately equal to, let's do the math here. I've got pi over n divided by the square root of pi over n. Well, I could simplify that just a bit more. I could say that that's equal to pi over the square root of pi, which is just some constant, n over the square root of n, which becomes pi times the square root of n all over the square root of pi. And of course, this is just a constant. This is just approximately equal to the square root of n. Wow, what a powerful stuff, man. Stirling's formula, I love it. This tells me that the original series behaves -1 to the n, 4 to the n, n factorial square all over 2n factorial. This behaves a lot like the square root of -1 to the n times the square root of n. Yippee-ki-yay. Winner, winner, chicken dinner. This tells you, of course, that it diverges, and that's it. That's why they pay me. Alright, we'll see you guys here next time. Peace.